So this script will run binary classification on a PCOS clinical dataset, comparing a neural network against a naive Bayes. First, I'll just show that the code works, where various figures will be generated that I'll discuss later. So the dataset is the PCOS full dataset from Kaggle, with 541 patients that samples, and each with 41 clinical features. PCOS stands for polycystic ovary syndrome. Data load in here, I'll first remove useless columns in terms of prediction, such as patient file numbers, serial numbers, and also if I left these in, the model could learn to associate specific IDs with labels it saw during training, which is essentially memorization, rather than learning actual patterns, which is what overfitting is. So this string to double conversion forces these to become not a number, so only valid numbers remain. So this class distribution shows 67.3 for non-PCOS and 32.7 for PCOS, which is roughly a 2-to-1 balance ratio, which is an important evaluation consideration because accuracy can be misleading in imbalanced datasets. Now for the pre-processing, there's 3 feature types, first being binary feature types where yes is 1, no is 0. There's categorical feature types, which is like the blood groups, and continuous features here defined as not binary and not categorical. It needs normalization, that is, you rescale the continuous numerical features onto a common scale. So this fold-wise pre-processing here is critical as I impute missing values and normalizing only using the training statistics, not the test statistics. As if I had the test statistics, the model would kind of be cheating. Same with the z-score normalization here, I calculate mu, which is the average, and the sigma, and then this line here uses logical indexing to prevent division by 0. Now for the cross-validation, I tested 3 k values, where the folds is 5, 10, or 15. I do stratified partition in here, or CV partition, with stratify set to true, which reserves the class ratios in each fold. Without this, some folds might have too few of PCOS cases, which skew the results. For selecting the optimal K, I use a stability adjusted score, which is accuracy minus half of the standard deviation, which penalizes high variance results because I want reliable estimates, not just high numbers that fluctuate. K equals 10 was chosen because it achieves the highest combined stability score. Whilst naive Bayes is stable, its accuracy is lower, and the neural network K equals 10 gives the best trade-off between high accuracy and a reliable variance. So the neural network architecture is pyramidal. The first 41 input neurons are defined here automatically. So the first in layer is 25 neurons, followed by a 12 neuron hidden layer, and then finally a single output neuron with a sigmoid activation for binary classification. And because the target variable of Y-train here is a single column of zeros and ones, the network looks at it during a train command and automatically creates one output neuron to match it. So the pyramidal structure forces the network to compress the information as the layers get smaller, so it can't just memorize, it has to learn patterns. 25 is roughly 60% of the input and 12 is about half of that. So I use patternnet here with train SCG to, which is scaled conjugate gradient, which avoids the computational costs of line searches that other training algorithms will need. So the max fail parameter is set to 20 if for early stopping patients, and that is if validation error doesn't improve for 20 epochs, then training stops. And this prevents the network from memorizing the training data. And importantly, test ratio is 0 because I already have an outer text fold from cross-validation, so this 80-20 split here is only for internal early stopping. Now for naive Bayes, I use Gaussian distribution for the continuous features, and this is justified in a feature distribution figure. You can see that I've overlaid the red Gaussian fits on top of the histograms, and so the BMI shows a reasonably normal distribution, whilst FSH and LH are right skewed, but Gaussian naive Bayes is quite robust to moderate violations of normality because it only needs the ranking of posteriors to be correct. So alternative distributions that could work include kernel density estimation for non-parametric flexibility or multinomial for count data, but for this mixed clinical dataset with continuous measurements, Gaussian is the standard and therefore the best choice. So as you can see, training is considerably faster than neural networks. As you can see in the results, naive Bayes is about 8 times faster. Now for the results, looking at the metrics comparison bar chart, we'll see that the neural network achieves 87.8% accuracy with an ACU of 0.945, whereas naive Bayes gets 84.5% accuracy and an ACU of 0.901. So NNN neural network wins on most metrics. So the confusion matrices here are interesting because the NN has 38 false negatives, whereas the NB has 27 false negatives. But in a medical context though, false negatives mean missing actual PCOS cases, which is clinically dangerous. So naive Bayes actually has better recall, which is 84.8 versus 78.7. However, the ROC curves show that neural network hugs the top left corner more tightly, indicating better overall discrimination. So the Bright score, which measures probability calibration, is 0.088 for neural networks versus 0.136 for naive Bayes. Lower is better as it indicates more accurate probability estimates. So the neural networks gives more reliable estimates, not just correct classification. Therefore, the neural network performs better overall, but naive Bayes is more computationally efficient and has better recall, which matters depending on whether you prioritize speed, interpretability, or minimizing mixed diagnoses. In conclusion, NN wins overall, but NB stays competitive despite its independence assumption.